asymptotic notations. Okay, asymptotic notations. So in our previous class we learned about what is meant by asymptotic, right? The definition of asymptotic and how to find the horizontal and vertical asymptotic lines for given function, right? So now we will try to understand what is meant by asymptotic notations in computers, data structures and algorithms. Okay. So for anything, for identify something, anything in this universe, we will have some identification for that object or for that thing or whatever it called. So for in our computer algorithms also, to represent the complexity, of algorithm, represent the complexity of your piece of code. So we will have use these notations, basically asymptotic notations. So we have three kinds of different types of notations we will represent. We can represent our time complexity of your program or of your algorithm or your piece of code by using these notations, basically big O, big alpha, big O, big alpha and theta. So before we jump into what are these actually, I just want to, we will try to understand by using some graphs so that we will learn a very proper way. I think so that every one of us can understand in easy way manner before jumping into the definition or equation of the omega, what is meant by omega or big O or theta. Okay. So every one of us now, I hope every one of us understood what are meant by functions, because we learned that, right? We learned what are the functions we have and how to plot those functions in our XY graph. Okay. So for example, we have 1 root n log n n power k power n. So we have different types of functions, right? This is we are learning these functions from our starting class onwards, right? We understood what are these meant by, and we understood how to plot these in XY graph, right? Everyone understood, right? Okay. So these are functions. So these functions, these are mathematical functions, right? F of x equals to root n, f of x equals to n, f of x equals to n log n, f of x equals to n power k power n. Okay. So these are mathematical functions. So why we are learning these mathematical functions and why we learned how to draw these mathematical functions in XY graph and everything, right? So basically, whatever the program you write in any language or any package, some set of lines, if you written some set of lines in any of the computer programming language, so this program requires some resources and some inputs, right? You will pass some input, and this whatever the instructions you written, those instructions will execute on top of based on your input n, and it will produce output, right? This is what computer will do. So why normally computers we prefer instead of manual human work? Because whenever we do manual work for one repeated action, right, there will be a chance to do a manual mistakes. Human can do a mistakes, but once you fix the program, once you written the some steps and if you provide it to computer, it always produce same output. There will be no manual work. That means what exactly we are doing? Automating the manual work into by using computer languages, right? Computer based on any language or package, whatever you call. But the main intention for our computers is to automate the work. Whatever we are doing manually, we are trying to automate that work. That's why computers are more useful. So when you are solving one big problem, instead of doing multiple times by solving, we will write one program so that the computer will execute every time based on your input. It will produce output for some time. So for some time, right? It will produce in some time. When you pass some input to your program, this will produce your output for some time. So this time is very crucial because we learned in our previous classes what is meant by problem and how much time we need to spend for each problem based on P, polynomial time, or non-deterministic polynomial time, or exponential time, or finite time, or some problems doesn't solve even if we have lot of resources like time, money, everything. So the crucial point is, if I for given input, my program, how much time required to produce an output. So this time complexity, of not only time, it requires what are it requires? It requires time, definitely, and it requires memory, CPU memory, right? Memory also required to run this, right? Resources, CPU, memory, everything will comes your computer configuration. The most configuration, the most performance it will do. But apart from this part is very crucial. Time is very crucial because we learn that what is meant by P, polynomial time, and PXP, right? So exponential time problems will require lot amount of time, right? Right. So now we are saying we require some amount of time to produce my output for given input n. So how you will represent this time for problem to problem, algorithm to algorithm? So to represent this time factor, we require some notations, right? We require some name. We require some approach to be well-defined approach to be. Everyone should, if everyone calls, represent that time factor or this, the how much amount of time, the complexity of your program, in some notation. The complexity means what is the complexity? Your time and how much resources your program is consuming. So to make sure everyone follows same way of representing the complexity, we have big O notation and big O omega, big omega, big O, big omega, and theta notation. Okay, so we will learn about this, what exactly meant by this. Each of them we will explore in detail, so don't worry for now. So now we understood functions and we understood why we required some notations to represent complexity of your program. Program means what? For example, I just want to tell you, you will write some set of code, right? Some set of lines. These lines will consist whatever based on your problem. You will write these statements will change, right? This is your program basically. So what is this meant by program? The program will be converted into binary, right? In whatever C# or Java or Python, whatever you write, or VB.NET, whatever language, JavaScript, whatever you will write. So this program will, the end of the day, before execution, it will convert into binary, right? binary, 1 zeros format, one binary string it will come. So your program ultimately converted as binary string, right? Binary string. So this binary string also, the end of the day will have some number actually. The binary string will contains 1 zeros, 1 0 0 0 1 1. So this your program converts as like this. But if you see this digits 1 0 0 0 1 also represent one number only finally, right? So let's imagine I have one function f of x. Any function you can take. Just for example, I am taking as 2x plus 3. For example, this is my function f of x, 2n plus 3. So my input is n. So let me mark it as so. For our understanding, to understand properly these asymptotic notation concepts, let's take the function f of x equals to 2n plus 3. This is my f of x function. So now every one of us know how to plot this in a graph, right? This is a graph. Okay. So this is our input n, and this is the time required to complete this function. Let's imagine, for example, in place of n, let I placed 1 here. So what is my output? 2 multiplied by 1 plus 3, how much? Equals to 2 plus 3, 5. Okay, so if I pass my 1 input, I am getting output as 5. Just imagine, for example, this is my 5. So this is my mark. Now I will pass 2 to this function. So instead of 1, I need to place 2 here. So 2 multiplied by 2, 4 plus 3 equals to 7. So for 2, what is my time I am taking? I am just taking 7. Let's imagine this is my mark. Okay. So now I will pass 3. 2 multiplied by 3 plus 3. 9. Okay. For example, if this is 9, this is 3, this is my 9. Now I will pass 4 here. 2 multiplied by 4 plus 3. 8 plus 3, 11, right? So now I will arrange this. Yes, we need to place the values here. That's it, simple. So now I got for 4, what is my value? 11. Let's imagine this is my mark. So we will do it for 5 also. Let's imagine 2, 5, 10 plus 3, 13. Right? So 2 multiplied by 5 plus 3 equals to 13, right? Okay. So for 5 this is. So now we plotted this function in n and t. For given this input, this is the graph I am getting. So if I increase input n, my graph also grows like this. Okay. So now what we will do is we will try to find another function. Let's call it as g of n. Okay. Let's call it as g of n, and we will multiply with c. C is constant, a positive constant. Let's imagine this is my another function g of n, and I am simply multiplying with a positive constant c. Where c is a positive number. Okay. So now I want to find a function. So that function will always falls under. Just try to understand. Now I have this function f of x, and I drawn this graph, and I got this line, right? Now I want to find a function. G of n, right? So that graph always falls under this area. not under this area. So if I find any function, I want to find a function that falls under this area, not below this. Okay, so let's try to find one function for this. Let's take, so my g of n equals to, so what is my f of x, g of x, f of x equals 2n plus 3. So I want to create a line, I want a line on top of this line, not below this. So now my goal is, I want to find a function. If I find a function, that function should always falls here in this area, okay. So now what we will do is, we will come up with some function based on this. So my f of x is 2n plus 3. What I will do, my g of n is 2n plus, I am just simply multiply with another n. So what exactly I done, I always get the value here only for passing same numbers. Let's try to find out where exactly this will fall. So now for 1, if I pass 1 here, what I will get, 2 multiplied by 1 plus 3 multiplied by 1. What is my answer? 2 plus 3 equals to 5, right? So for one value, I got same digit. If you observe, for one value, I got the same value as f of x and g of x, right? Okay. Now what we will do, we will pass next value, input 2. Okay, understood, right? So initially when we pass one value here, what value I got? For f of x, 5 I got. Same way, if I pass 1 here, I am also getting the same value as 5. Okay. Now I will pass. Now we will pass second 2 as input. So 2 multiplied by 2 plus 3 multiplied by 2. So 2 multiplied by 2, 4, plus 3 multiplied by 6. What is my output? 10. So when I pass 2 value to my g of x, I got the value 10 somewhere here. Okay. So now we will pass 3. Now we will pass 3 value here for g of x. 2 multiplied by 3 plus 3 multiplied by 3. 2 multiplied by 3 is 6. 3 multiplied by 3 9 equals to 15. So for 3 I got 15 value. Let me increase this. For example, this is 15. For 3 I got this. Now we will pass 4. 2 multiplied by 4 plus 3 multiplied by 4. 8, 2 4s are 8 plus 12 equals to 20. So for 4 input for g of x, what is the value I got? 20. Okay. So now we will try to draw. This is my g of x. So now what we will do is, for this g of x, we will multiply with one constant. G of x multiplied by with c. In this case, let's imagine constant is one value. Okay, just imagine our constant is positive 1. So this c value is always 1. Okay, even if you multiply it and if you try to plot, we will get the same value. Just I will repeat for our understanding. If I pass 1 here, 2 multiplied by 1, 3 multiplied by 1, and 1 multiplied by c, 1. So I get 5 only. So if I pass 2 here, 2 multiplied by 2 plus 3 multiplied by 2 and 1. What is my output? 4 plus 6 multiplied by 1. So I got 10 value only, right? This is 10. See, okay. So now for given f of x, I found g of x with another positive constant. When I multiply with this g of x, I found I am able to draw this graph, right? This line. I am able to find this line, and where exactly this line is falling under. So this line is falling above or nearer to this f of x. This line, if this line, right? This line is falling under this line. So clearly just try to concentrate here. We found g of x for given 1. If I pass 1, both values are same, right? For f of x and this complete statement, right? These two things given me the same value 5 for input 1. So after that what happens? After that, if I change incremented to 2, my f of x given 7, my g of x multiplied by c given 10, right? So this point, after this point, that means after this input, this line, after this input, this line falls above, falls upper than this f of x, upper than this f of x, right? So this we will call it as input, we will call it as n0. Okay, this is upper bound to this f of x, right? This is upper bound to this f of x. So this line can be false here, here, or here, or very nearer, or we can say this line also upper bound for that same line. Okay, so now I hope everyone understood, right? First, what exactly we done? We derived one graph, we plotted one line in this graph for this f of x for given input n, and what is the time it is taking. After that, what exactly we done? We find another function g of x, and we are multiplying with some constant, okay, a positive constant. So after that, what exactly we done? We found n0, find n0, and we passed every input same input. What exactly we passed here? We passed the same input here, and we found this line. So this line, what we are saying? G of x is always greater than or equals to f of x for all c and n, a positive number, okay, such that n is greater than or equals to n0. So this we will call it as big O notation. Big O notation. So if everyone understood, we will write that equation, right? We will convert these statements, this picture into a formula or one definition of big O notation. So what is meant by big O notation? When you have a f of x, that f of x is lesser than or equals to g of x multiplied by constant, such that n and c are always positive numbers, and n is greater than or equals to n0. So now in this case, what is n0? 1. After 1, these for every input, my graph, this statement, this conclusion, these variables, set of variables produce upper bound to my graph. Okay, so this is called big O notation. Big O notation. So we will convert this into a formula. I will erase this. I hope everyone understood, right? Okay. The function f of x equals to big O of g of n, okay, if there exists is positive constants C and N, positive constants C and N, said that f of x always lesser than or equals to C constant multiplied by g of x for all n is greater than or equals to n0, right? So in our previous case, based on this, what is our f of x? F of x equals to 2n plus 3, right? So in previously we drawn that line. So our this f of n is 2n plus 3. I will write here 2n plus 3. So this is C. In our case, in our example, we given one constant one. G of n is 2n plus 3n. This is what we took an example for to satisfy this condition, and for n is greater than n0. In our case, n0 is what? 1. Right? So this is the definition of big O notation. So if you understand, we will, if you are okay with this, we will try to explore some more thing on what is exactly this mean. What is my constant 1 multiplied by g of n, right? This is C. In our example, C is 1 constant multiplied by what is our gn? 2n plus 3n, right? This is our next function, C multiplied by g of n, and this statement is always greater than or equals to f of n, right? So here, if you see here, what will be my output actually? If I can add this, right? 2n plus 3n, what is my output? 5n, right? So 5n here comes. So if you observe, 1 is a constant, right? 1 is a constant, and 5 also another constant, right? 1 is a constant and 5 also constant. It won't change based on our input, but what exactly it will change? N always changes, right? If I pass 1 here, it will give some value. If I pass 2 here, it will give different value. If I pass 3, but instead of, if there is no n, irrespective of my n, input n, it always produces 5 only, right? But whereas because of this n, this factor will change, grow actually based on this. So why I am explaining this? Because there is one reason. See, this is one constant, and this is one constant. So while writing f of x equals to big O of g of n, so while writing, instead of writing 2n plus 3n or 1 multiplied by 5n, I want to make this as more simple by eliminating these constants. You can ask me why we should eliminate, right? Why should we eliminate? Those are also contributing your time factor, right? But why we are eliminating? Because let's imagine, for given some values 1 to 10, input n as 1 to 100 or 200, these factors will be significant. But when I am increasing this value n to 1 lakh or 2 lakh or more number, if I take a number with big input number, then this constants won't make that much significant actually. But when you take a small number input, then these constants will be a significant role they will play. But when you take a huge number of input n, these factors won't be that much significant when you pass on through n number, right? When you increase the n number. So that's the reason we always interested in the degree of n. So we can eliminate these values because when we increase the input number more and more bigger value, then the significance of these constants will be very less. That's the reason we always look for these n facts, n degrees basically. So if I remove these two things, what I left? I left with n. So this can be represented, n can be represented as n power 1, right? So I can call this as n power 1. So that what is my degree? Degree of this n is 1. So while writing my f of x equals to big O of g of n, I can write like this. F of x, my f of x is what? 2n plus 3. For this f of x, what is my g of n? Big O of g of n? I can write g of n is what? The degree of highest degree is 1. So I will eliminate these constants. I will keep only my n here. So this is O of n, big O of n for this f of x function. So I hope everyone understands, right? This is very interesting. I know you people will enjoy this. So we can f of x equals to big O of g of n, right? So in this case, what is my f of x? 2n plus 3 equals to big O of n, right? This is what big O for this f of x, right? Okay. Now we know 1 is a constant time. If your program is taking, irrespective of your input, if it is taking constant time, we will write this as 1 constant time it is required to execute your program. So we have other functions also, like log n, root n, n log n, n power k, k power n, right? These things we are learning from starting onwards. So these are our functions. So this one is always lesser than log n. Log n is lesser than root n is lesser than n is lesser than n log n is lesser than n log n is lesser than n power k is lesser than k power n time. So if you know k power n is exponential time, n power k is polynomial time, right? So in our example, where exactly we landed? We landed here, n. So for this function, for this f of x, this is big O of. This is what we are saying. This is upper bound for this function. So when I say n, this n is lesser than these functions, right? That means these things also can be considered as upper bound for this function. That means what exactly I am saying? For this 2n plus 3, I can write big O of not only n, big O of n log n also I can represent, or big O of n power k also I can mention, big O of k power n also can be upper bound. These are upper bounds for this function. Just we will try one simple same thing, we will do it. So what is my f of x? 2n plus 3. So 2n plus 3 is always lesser than or equals to. So now what is my g of n? G of n is what is we use 2n plus 3n, right? So instead of n here, what we will do? I will use n log n. 3 log n, okay? Or I can use n power k, okay? 2 power n power 3, for example, n power 3. Or I can use 3 multiplied by 3 power n. So these all, when you replace here one of these things in your g of x, it always produces the greater value compared to your f of x. Greater or equal value when you place from this point onwards. That means from this point onwards, these all functions are upper bound for this function. Right? So, if you see in this graph, if this is my f of x, so where n will fall? We've seen that already. Our g of n is like this. When you do it for n power k, instead of n, just place 3 multiplied by 3 n power 3, you will get like this. Or 2n plus 3 multiplied by k power n, 3 power n. You will get one line like this. So for this function, these are all upper bounds. We can say these are all upper bounds, not only n, but these are all upper bounds. But it is very good to tell us what is the nearer upper bound for this function. What is the nearer upper bound for this function? Nearest is upper bound is what? N. Right? So it is, we will always try to represent the nearest upper bound for any given function. So this is overall concept of big O. Okay?